mental at the moment. That is a lot of work to be doing in a short amount of time. Okay, probability is going to be in paper 1. And it's not a huge section, but it's a section where it's nice to get as many marks as possible, because it's like you're guaranteed to get some questions that are exactly the same as each other. And that's kind of what we've got to rely on. So let's sort of start by getting an idea of things. I want to hear from you. So in the chat, who can give me a very, very easy, basic definition of what probability is? Don't give me like fancy words. Give it to me in like a nice, easy to understand way. What is probability? Chance. I like that. Good. Yeah. Chance, possibility of something. Good. I like that. Good. Okay, beautiful. So if we're talking about the chance of something or the possibility of something, and where we have outcomes, what could my range of outcomes be? What do I range from? What's the lowest I could be, and what's the highest I could be when it comes to probability? Good. I go from 0, so from something never happening, all the way to what's the maximum probability can be? Beautiful. 1. And that's certain. Good. Or we could do it as percentage. So for probability, we either work in decimals or fractions or percentage. So never would be 0% and certain would be 100%. Beautiful. Okay, so can you think of something that has the probability of never happening? So of 0%. Yeah, I mean, maybe with AI now we might be in a different situation, but yes, pigs flying. Good. Pigs flying. There's a there's no chance that you're going to look out your window and you're going to see a pig flying at the moment. What is something that we can say with certainty? What is something that is 100% certain that will definitely happen? Yeah, we do. But what if we didn't have food? We might not have food one day. So that's not always going to be 100% certain. Weather will change, so there will be weather. Oh, we're reaching for the stars here. I will get 7 distinctions. I was thinking more like the sun will rise in the morning. So something definitely that we know for sure. There's no variables, no chance of anything going sideways. We know 100% that that's going to happen. Although I do also 100% believe that you two are going to get your 7 distinctions. Okay, so that's what the idea of probability is. Next thing we're going to chat about is what an experiment is. So not in terms of like science experiments, an experiment in terms of probability. Any suggestions? Let me give you some Earth human minutes to think that through. Yeah, kind of, Sanele. That's actually very, very true. Yeah. Also, can you see, Leah? I like that a lot. Basically, it's just an activity that has different possible outcomes. So, like, let's actually just write it like that. An activity which has different possible outcomes. So it's kind of like a way of testing probability. Like an example would be tossing a coin, for example, or if you rolled a die, those would be experiments. Okay. And then a trial is kind of like part of an experiment. So in an experiment, so let's say our experiment was tossing a coin. Every time we tossed that coin, that would be a trial. So each of those trials then make up your whole experiment. So in an experiment of tossing a coin, each toss is a trial. So one experiment has many different trials. Did it really? That's crazy. You did. You got the best of both. Okay, outcomes is something that we've now sort of used the word a couple of times in talking about it. If we're using this experiment of tossing a coin, and so each toss is a trial, what would be my outcomes of that? So what are the outcomes of an experiment? Remember, don't overthink it. We're trying to make it as simple as possible. Yeah, it's the results. So it's the possible results. So in the experiment of tossing a coin, my outcomes would be heads or tail. Except if you're a boo, and then you get a sideways. Yes. Okay. All right, can I get a thumbs up if we are happy with these sort of words so far so that I can get an idea of where we're at? Okay, I'm seeing thumbs up. Great, great, beautiful. Okay, we've only got a couple more words and then we can start playing with some numbers. I will zoom out so you can get all of these as a screenshot at the end. All right, what would be a sample space? So kind of think about in terms of outcomes and think if you can give me a nice way of talking about what a sample space would be. Yeah, I like that. Number of events present. I like that. It's the total. It's going to be our total number. So for us, it's going to be the total number or the total list or set of all possible outcomes. So as an example, let's say that I toss 2 coins in the air. Okay, so my experiment is that I have tossed 2 coins in the air. My outcomes, or the sample space that I could have, is I could get heads on both of my coins, or I could get head on one coin, tails on the other, or I could get tails and heads, or I could get tails and tails. So I have 4 different outcomes. And we would write this like this. That's an S. I know my S's look like 5. And all that is meaning is that the number of outcomes in my sample space is 4. So this is the important thing to take from that. So that's looking at all of our different possible outcomes that could happen. You can absolutely get this from a tree diagram, which we will be doing next week, Tuesday. So today we're doing introduction to probability. Thursday, we're going to do Venn diagrams. Next week, Tuesday, we're going to do tree diagrams. And then we're going to put it all together for some past paper questions. Okay, and the last word that we're going to chat about is event. I'm very curious to hear what your definitions of that is going to be. What is the event? Yeah, I like that. Set of outcomes. It's the outcomes that we are interested in. So it's the ones that we would determine as like a favorable outcome. So or like the favorable outcomes. So basically what we see is, I will explain this, don't you worry. And then that's going to be oh, that line is very wonky. Okay, so let's say hypothetically that my event, or the thing that I wanted, my favorable outcome, was that in this experiment where I tossed 2 coins up in the air, I wanted both of them to come as tails, so to land with tails. What would be the probability of that event occurring? Well, the number of outcomes in the event is 1, and the total number of outcomes is 4. So we can leave it as a quarter, or we can make it a decimal, or we can make it a percentage. But all of those would be the probability of my event occurring, which in this case was to get 2 tails. So the other way of writing this, which is what you'll see on your formula sheets, which looks a little bit scary, but it's not scary at all, looks like this. And that's saying exactly the same thing. So this is saying the probability of the event occurring. This is the number of times that event happens over the total number of outcomes. And that's kind of like that's honestly, if you can understand this, you understand the bulk of probability, to be 100% honest with you. For screenshots, do you want me to zoom out the whole page, or do you want to do it in halves? Let me know. Half. Okay, first half. And second half. Okay. Now I have helped you with a lot of this. So let's kind of break this question down a little bit, and then I'm going to let you try it by yourselves. In an experiment, a coin is tossed. So if we have a coin that is being tossed, our options are heads or tails, and a dice is thrown. So there my options are 1, 2, 3, 4, 5, or 6. A favorable outcome is obtaining a tail and an odd number. Exactly, we're going to do a contingency table. So we have our die, and then we have our coin. So think about this as 1, 2, 3, 4, 5, 6. And then for coins, we have heads or tails. So in this first block, that would be the same as flipping heads and rolling a 1 on a die. And this would be flipping tails and rolling a 1 on a die. So this is called a contingency table. And we use it to see what our sample space is. Yeah, sure, Desdemonia, no problem. Hi, Leander. Okay, we've just been doing an introduction to probability. Okay, so first mission is to fill out your table. You don't have to draw it beautifully on your side, but just get an idea of what it looks like. And then you're going to see if you can write the set A of favorable outcomes. And I'll show you how to write that if you're struggling with anything. I will give you first have to fill in the table. So I will give you 3 full human Earth minutes. And I'm going to add another question. So set A is the set that we care about. So it's our It's our favorable outcomes. We're going to write it in a bit of a fancy way. But I want you to first try and see what you get. And then I promise I will go through it. Do you guys know that with die, the opposite sides of a die always add up to 7? So if you're looking at like number 6 on the die, then the other side will always be a 1. And if it's a 5, the other side will always be a 2. If you didn't know, now you know. Yes, the answer is a quarter. Yeah, I promise, can you see? You can go check any die. Always add up to 7. See the fun facts you learn in maths. So you can try and like gamble with people and say that you can guess what number is hidden. If you like roll a die and let's say you're looking at a number 3, you can say you can guess the number that's on the ground and you know it's going to be a 4. See if you can get some chocolates that way. Okay. So first goal is we need to fill in our contingency table. So this is going to, let me get back into our color mode. Heads and a 2, tails and a 2, heads and a 3, heads and a 4, heads and a 5, heads and a 6. Okay, so now we are going to have a look at what they said. They say that the favorable outcome is obtaining a tail and an odd number. So that's a tail and an odd number. That's a tail and an odd number. And that's a tail and an odd number. Those are my only 3 favorable outcomes. So if they're wanting us to write it as set A, we have to write it in a bit of a fancy way. We're going to say A is equal to, and then we're going to do curly brackets. And we're going to write exactly what those outcomes are. So tails and a 1, tails and a 3, and tails and a 5. And that is my set of favorable outcomes. So those are my 3 favorable outcomes for set A. And set A is when we have a tail and an odd number. So whenever they want you to write a set, that's how we're going to write it. And the probability of this outcome is we think about what is our favorable outcomes. There are 3. My total outcomes, there are 12. So that would be the same as 1/4 or 25%. Okay. Any questions? Let me know. Can you see? That's a great question. I think generally the idea with fractions is always to simplify as far as you can. So if it can be simplified, simplify. Okay. It does indeed. Yes, we will get there. Contingency tables are a long way around of doing that. Yeah. And that's why tree diagrams are so fun. Okay, so these we kind of spoke about a little bit just now, the different types of events. We spoke about if something is never going to happen, if something definitely is going to happen. But let's kind of just give them a few sort of pieces of information. So impossible events are things that have a probability of 0. Okay, so as an example, like you suggested, looking out your window and seeing pigs flying, that would be something that is not going to be happening. It could also be something like, if I rolled a die, what would be the probability of rolling an 8? That is something that is impossible. It's something that cannot happen. Unless you're playing with like a Dungeons and Dragons. What are those? Deco. Oh man, I've forgotten the name. It's 12-sided die. I've forgotten the name. We will deal with mutually exclusive. Don't you worry. Yeah, 12. I have one. I'll go grab it. An even chance of events. That is when we have 50% of something happening. So it's an even chance of something happening, 50-50. I know Abu is going to argue with me, but it's the idea of, if you toss a coin, you can either get heads or tails. You can get heads, you have 50% chance of getting heads, and you got 50% chance of getting tails. I know. I said you would argue. Certain events are if something has a full probability of happening. So it has a probability of 1. Or 100%. It's okay. Thanks for coming. So we had some examples of getting 6 distinctions, which I liked. I'm going to go with a more boring one, that the sun rises every morning. That is a certain event, unless we are hitting an apocalypse, in which case we would be quite sad. Okay, then we get 2 special types. We get events that are called mutually exclusive and complementary. Mutually exclusive events, who can give me a nice definition of that? I will go and turn the light on and go grab a 12-sided dice while you write me definitions of mutually exclusive events. And I will be 1 minute. Yeah, they have no intersection. I like that. Separate with no union. I love that. This is a double-sided dice. I don't know if it's, you can see. Is it blurry or is it okay? That's what it looks like. It is cool. Got a whole bunch of different die in here actually. What's the fun of being a maths nerd if you can't be nerdy? So this die goes up to 8. So it's like little, kind of looks like a, what does it look like? A spinning top. Yeah, like a diamond. Okay, so mutually exclusive events. It's when two events can't happen in the same trial. So if I roll a die, I can get 1, 3, 5, or I could get 2, 4, 6 if I was thinking of odd numbers or even numbers. But I can't have an odd and even number. So something like that. Can't pick an odd and even number at the same time. So they have 2 separate events. And in order for things to be complementary events, they have to be mutually exclusive. And a complementary event is when it's not, it's the same as not obtaining that event. So for example, complementary events would be like getting heads or tails. So if I don't get heads, I'm going to get tails. They are complementary. If you don't get the one, you're going to get the other one. And if none of this is making sense, you need to let me know in the chat or put your questions in there so that I can help. Yes, very much so. Just gonna zoom out quickly. If you wanted to get these words, you can take a quick screenshot. And all of this results into that same formula we spoke about earlier, which is the probability of an event occurring is the total number of favorable outcomes over the total number of possible outcomes. And that's kind of like I know I've already said it, but like if you get this, that's the most important thing to get when it comes to probability. You're looking at the chance of something happening. So we're looking at what is the chance of my favorable thing happening out of all of the possible outcomes I could get. Exactly, Tboko. Yes, the sum of events need to equal 1 in complementary events. Because if the one doesn't happen, the other one has to happen. Okay. Let's try a nice, easy question. I'm just going to go up to D to start. Okay, so for the first part, if we're trying to write down the sample space, they haven't told us to write it in any particular thing, so we're just going to call it S for sample space. And if we're writing down the sample space of a fair die that's being thrown, our options are 1, 2, 3, 4, 5, or 6. So my sample size is 6. Just writing out the list, just because it can sometimes be a weird format. Eating spicy. Okay, don't overthink these questions. They're not nasty. Can you do B, C, and D for me? And then we'll do E and F. We'll do another question. We'll have a quick chat about something, and then I'll give you some more questions. Let me get all of your questions here. So E and F. There we go. Yeah, see guys, probability is fun. It's easy peasy. Oh, sorry, bit of a spelling error here. So the probability of us getting a 5, there's a 5. So our probability of getting a 5, our favorable outcome is 1 out of 6 total outcomes. Determine the probability of getting an odd number. So the probability of getting an odd number would be 3 out of 6, or half. If event E is getting an even number, determine the probability of event E occurring. So the probability of event E is also 3 out of 6, which is also a half. So that makes these two complementary. Because if we add them together, we get 1. Determine the probability of getting a number greater than 6. Would be 0. That is impossible in a fair die. And determine the probability of getting a number less than 3. That would be 2 over 6, which is 1 over 3. Hopefully we are finding these nice and easy. That is my hope. Teboho, that's so exciting. Well done. Kimberly, you can absolutely screenshot. Let me zoom out so you get the question. Guys, so many achievements in the class today. Well done. That feels like there is a story behind that, Abu. In an experiment, 8 balls numbered from 1 to 8 are placed in a bag. There are 5 questions to do here. Nice, easy ones, nothing too hectic. Give it your best go. Start by writing down your sample space and then getting your answers. And then we're going to have a quick chat about something. We're going to do some more questions. So, Uyana, when they're asking for the sample space, we actually need to write down all the different options in that sample space. So we can't just say that our total number is going to be 8. We actually need to say what our possible options are. If you're wanting to say 8, you can write it like that. So you're talking that you're saying your whole sample size is 8. Okay, I'm going to leave you a couple more minutes to finish up, and then I can go through these answers. Okay, let's go through these answers. All right, if A is the event drawing a prime number, what is going to be my answers? What are my prime numbers? Do we remember prime numbers? Some of the answers are telling me not. Oh, sorry, excuse me, guys. Exactly, it has factors of 1 and itself. So 1 is not a prime number. So our prime numbers here are 2, 3, 5, and 7. So the probability of A would be 4 out of 8, which is a half. Thank you. Okay, if B is the event of drawing multiple, yes, yeah. B is the event of drawing a multiple of 2 to determine the probability of B. So multiple of 2, 2, 4, 6, or 8. C is the event of drawing an odd number. So odd numbers, we're going to have 1, 3, 5, 7. And yes, absolutely, Uyanda, these are complementary. So if we don't get one, we're going to get the other. And D, event D is the event of drawing a number greater than or equal to 6. So that's going to be 6, 7, or 8. So that gives us 3 out of 8 possibilities. Not so bad. You want a screenshot? You're welcome to take one. So this brings us to a quick conversation. We have 2 different sort of types of probability that we work with. The one is called theoretical probability, and then the other one is called experimental. Who thinks that they can tell me what those 2 different things would be? No idea. Okay. So theoretical probability, let me take it to you like this, Boho. I've told you, if you flip a coin, you have a 50-50 chance of getting heads or tails, right? Okay, so we know that. Theoretically, we know that. So theoretical probability is when we use logical thought to determine the probability. So as an example, I have 50% chance of getting heads, 50% chance of getting tails. However, if I was in an experiment, so I'm now tossing this coin, what happens? Do we always get, like, if I toss a coin 10 times, am I definitely going to get 5 heads and 5 tails? What happens if I do an experiment with 5 tosses versus 10 versus 100 versus 1,000? So in experimental probability, we use trials to determine the probability. But in order for exactly, the results may vary a little bit. But so in order for us to be as accurate as we can be, we need to have lots and lots and lots of trials. So you need to have lots of trials for it to be accurate. So as an example, if I toss a coin 10 times, let's say I get 3 heads and 7 tails. So that's what I would be looking at. If you tossed a coin 1,000 times, you actually are going to get closer to 500, 500. It's just the way that it's going to end up working. So the more trials you do, the closer you're going to get to that theoretical probability. Okay. Now I have a fun question for you. Who has heard of the Monty Hall problem? So Kanyasile, it would depend on how many trials you've done in your experiment, but then it would affect that probability. The Monty Hall problem. The Monty Hall problem looks like this. Okay. I am a game show host. And as a game show host, I am going to give you 3 doors. Behind one of those doors, there is a car. Behind the other 2 doors, there are goats. And you are wanting to win a car. So, yes, audience applauses. Thank you. Okay, so Uyanda, which door would you like as your game show host? Which door would you like to choose? A, B, or C? B. Okay. What's the probability that you have picked the one with a car? So just so you all know, Uyanda has chosen B. There is a 1/3 chance that he is getting a car. Now, as a game show host, I have decided I'm going to be very kind to you, Uyanda, and I'm actually going to turn around door A, and I'm going to tell you that there's a goat behind door A. So now I've given you that piece of information. Now that I've told you that, would you like to stick with the same door, or do you want to move to door C? Why are you sticking to your door? And I turn around door B, and unfortunately, Uyanda, you have won yourself a goat. I'm so sorry. You've won yourself a goat. The car was hidden behind door C. I'm so sorry. But don't worry. It's okay. You will be okay. The Monty Hall problem is actually, it's quite weird. It's quite a cool thing. And there's some mathematicians who go very deep into this. I'm just going to explain it very, very briefly. But when you're given this choice, if you have been given a choice of 3 things and you know now that the one is wrong, it's actually probability-wise in your best interest to change doors. So by going to door C, because we now know that the goat was behind door A, you actually have a 2/3 chance of getting the car by moving to door C. So, the only thing the Monty Hall problem helps with is thinking in mathematical confusion and using probability in a weird way. And if you ever land up on a game show and they ask you if you should change the door, my suggestion is to change the door based on the maths, because your probability shifts from 1/3 to 2/3 by changing. And that is the Monty Hall problem. You know what? I don't know who Monty Hall is either. He must be a mathematician, though. Okay, we've done similar ones to question 1. So let's start with question 2 and question 3. Okay. Question 2. A letter is chosen at random from the word probability. What is the probability that the letter chosen is B? What is the probability that the letter chosen is a vowel? What is the probability that a consonant is chosen? I know that these seem easy. These are straight out of exams. Sometimes you fall with your bum in the butter with probability. And 2 is talking about a pack of cards, but we will get there after you have done the first one. Oh, sorry, 3. Good. We do a count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Probability that a B is chosen. We have 2 B's in the word probability. So that is 2 out of 11. We should actually probably write it with probability of B. I'm being lazy, guys. Probability of getting a B. What is the probability that the letter chosen is a vowel? I've got 1, 2, 3, 4. Probability of a consonant. These two are going to be complementary. So we can just see that that's going to be 7 over 11, because if it's not the one, it's going to be the other. Okay, I know not everyone plays with cards, so let's just quickly talk about a few things. How many cards do we have in a deck of cards? Good, we have 52 cards. And we have 13 of each suite. So we have 13 hearts, 13 diamonds, 13 spades, 13 clubs, 13 of each of them. We go ace, 2, 3, 4, all the way up to 10. Then we have jack, queen, king. These are considered the face cards. We don't include jokers when we deal with probability with packs of cards, unless they specifically say so in the question. So if they're giving you a question with a pack of cards, it's always going to be 52. There's normally 2 jokers. You are welcome. And your red cards are your hearts and diamonds, and your black cards are your spades and clubs. Okay, I'm just going to start putting in the answers as I'm seeing them in the chat. Probability of drawing a queen, absolutely 4 out of 52, which is 1/13. Probability of drawing a red card, that would be half of our pack. So you can just go straight to saying half if you would like to, or you could say 26 out of 52, which is a half. I'm very curious to see what your answers for D is. Probability of drawing a black 7, so we can get a 7 of spades or a 7 of clubs. So there's 2 options out of 52, which would be 1 out of 26. Okay. And for the last question for the night, if the first card drawn is a red card, okay, so I'm just going to write this out as we go. So we've drawn a card, that's a red card. And another card is randomly selected without replacing the first card. So now I only have 51 cards because I've already removed one card. What is the probability that the second card drawn is black? I still have all 26 of my black cards. So this would be the probability of drawing a red card and then a black card. Well, no, yes and no. Let me not write it like that just yet, though. For the moment, we'll just keep it like that. So we can just keep it as 26/51. If you would like a screenshot, please feel free. And then I'm just going to go back to the lesson for Desdemonia for the screenshots. But otherwise, guys, well done. First day of probability done and dusted. On Thursday, we start the fun stuff. Thursday, we start Venn diagrams and then tree diagrams, and that's when probability gets interesting. Yay. But you did very well. You started off strong. I'm just going to pop up for Desdemonia quick. That was the first half. Yes, don't worry, I haven't forgotten you. Bye, everyone else. If you're done, you're welcome to